So this is not something you would probably normally talk about in an engineering context, but this whole project comes up in a way that allows us as a group to fund this project. So we will pay for it, and we will own it, and we will maintain all the systems for the next 10 years. And the way we get paid is we are proving a certain amount of savings to the district, and the district is sharing that savings with us. They keep some of it, and they give us some of it. And that we use that money to pay down the money we borrowed, to pay ourselves, pay our engineers, pay our insurance company, pay our lawyers, pay our accountants, pay everybody. And what that allows us to do is at the end of the 10 years, we turn the system over to the school district and they get it. But the beauty to the district is it costs them nothing on day one. All this stuff is going in, brand new equipment, goes up, doesn't cost them anything. We are able to get all these grants from the federal government because we're a for-profit business. None of those grants would have been accessible to the school. And we are responsible for operating and maintaining the system. And we need to be here for 10 years because the school district doesn't pay us until we prove that we've saved them the amount of money that we said we were going to save them. So all of these systems, I'm just going to use some numbers to illustrate. We put this in. The school district is paying $1.7 million for energy right now for these two buildings. If we save them $200,000 in costs, they give us a portion of that. We pay off our bank loan and everything like that. So the school district will actually see its energy costs go down a little bit right off the bat, but they get all this brand new equipment for nothing. All of that is proven out by the engineers' work. They have to look at the energy loads, the heat loads, the capability of this equipment, the data from climate and weather stations to understand and take a guess, well, an educated guess, at what the average system performance is going to be. So if that would have been messed up by the engineers, the entire project would collapse. And so engineering is not just about designing a system and making sure that things meet and satisfy code requirements, but also it becomes the fundamental underpinning of our financial results. I'm going to skip through this. So there are 4 primary engineering roles in this project. What is called energy modeling, electrical, mechanical, and structural. And what I'll show you first is the energy modeling. This is a graph of the Exeter High School's electric use for an entire year. This is, and it's kind of gets a little jammed up, but the points on the graph are every 15 minutes. So there's several thousand points on this graph. And so you can see that even at night, the school is still using somewhere between 160 and 180 kilowatts. And so it's funny, you can see how it goes up and down and then up and down. That's the week. So during, this is during the week, and then on the weekends it stays down, and the week during the weekends, and then we don't know what was going on in the end of June, but there was a lot of power being used in this week in June, around June 10th. And what you can see here, these drops are power outages. And then what you see at this big drop, see how wide the drop is? That's the ice storm, when the power was out for 3 or 4 days in December. So this is what the engineers had to use and say, okay, if we're going to put a solar array on the Exeter High School, we need to make sure that it meets the Exeter High School demand and doesn't go over it. It wasn't a big problem because Exeter High School is using a lot of electricity. We then take that data and we use computer programs basically to model out the way the electric works. And a lot of the things you can buy for thousands and thousands of dollars. People can make up their own using spreadsheets, or you can get one from free from the Canadian Department of Natural Resources, which was put together in conjunction with NASA, and it is called RETScreen. You can download it off the internet. It's great because it has 2 modes. It has kind of a real simple mode, and then it has a real complex engineering level mode. We use the simple mode to just come up with ideas, and then we use the complex engineering mode to get to the point where we're ready to make decisions about what kind of system we're going to put in. Let's go backwards. This, remember the graph with all the red lines up and down? This is one day. And so you take that line, it looks spiky because it's it's a whole year. When you blow it out, you start at midnight, and then everybody starts showing up. The times aren't really here. Everybody shows up at 5 in the morning, and everybody starts turning on their computers and their lights and everything. And then while the students are there, this is 2:15, students leave, a lot of stuff goes on. This is when the faculty and the staff leave, and then everything gets turned off, and then it just kind of sits for the rest of the night. And then I would imagine that they have some kind of building control system that shuts other things down at like 10 o'clock. And so then it just sits quiet until it starts to get, this is February again, so the heat system comes on, you got the pumps running and the fans running, and then you get this. And so this is what your daily electric load looks like. And so the importance of this load profile is it mirrors the sun. So the sun comes up in the morning, in solar, it starts generating, and then when the sun goes down, it goes down. This is a perfect kind of load that you want to see when you're trying to design a solar array to provide power for a building. That data gets pumped into the model, produces all these graphs. I'm going to oversimplify this. If at some point in the future we want to work on an energy model, I'm happy to do that. It's a very easy thing to do. I just want you to see what it looks like so that you can see what we did in some of our background work. We model out the heat plant. This is the results of the carbon offsets. So the model will take data for the grid or the power production grid of the United States. It shows you how much carbon per megawatt comes out. You estimate how much losses come off the lines, and the model will tell you, okay, this system that you're modeling will reduce the output of greenhouse gas emissions by 81.9 tons or 16.7 cars. This was not the SAU system. This section, the software already has all the weather data in it from various locations all over the world. We used, luckily for us, there was one very close, we used Pease Air Force Base. It has 30 years of climate data, and so it averages that and then uses that, and that's how you determine how long your heating system runs and how much air conditioning you need. And then you get to these final pages, which get really busy, and then you end up with this page. And this is actually a house, a home system, a solar system for a house, a solar hot water system. But what it shows you is, okay, if I'm going to invest $15,000 in a solar hot water system, when is that going to pay off? Meaning, when do I save enough money to get my $15,000 back? And if you've done everything right in the model, it'll tell you exactly when that is. And for this system, it was 4 years. And you can put in all kinds of information like tax credits and tax depreciation and the cost of the system. And then what you see here is like a bump on a maintenance. And so we assumed for this model that at the 10th year there would have to be some maintenance done to the system. So you see how the line goes down a little bit and then it goes back up. And then if it's in a 20-year system, if you put on this solar thermal system on a house, at the end of 20 years, you will have saved $70,000.